Hello, everyone. Today we're going to talk about topic 2.8, tonicity and osmoregulation. One of the important, there we go, let's make this bigger. Two important things are involved with our osmoregularity. We've got two equations, so we've got a little bit of math this time around. There's water potential. The water potential value of a solution is a quantitative value that is used to determine the direction molecules will move across a membrane into or out of the solution. Water moves from an area of higher water potential or higher free energy to an area of lower water potential, or you could say it is lower free energy. Osmosis is going to be our movement of water molecules from a region of high water potential to regions of low water potential. In an open system at room temperature, pure distilled water has a water potential value of 0 because both the solute and pressure potentials are 0. As the concentration of dissolved particles in the solution increases, the water potential value decreases. So our water potential is a function of two things, the solute potential and the pressure potential. We're going to look at solute potential first. Now with these equations, they are on your AP Biology formula sheet. You do not have to have them memorized. On the right over here, we can see this is what's on the AP Biology formula sheet. A reminder, this formula sheet is posted for you in Schoology on our resources page. You can also just always get it by Googling AP Biology formula sheet. So first we're going to look at the solute potential. This is the formula to calculate osmotic potential, but now we call it solute potential. And we've got a few variables. If we look at our equation, solute potential equals negative I CRT. I stands for the ionization constant. So this is just how many ions there's going to be. If something does not ionize, like sugar, so really anything that's nonpolar, it's going to be 1. If it's something like salt, sodium chloride, that would break up into 2 ions. So now our number is 2. C is going to be the molarity of the solution. R is the gas pressure constant. It's a constant. It's always going to be 0.0831 liter bars per mole Kelvin. This is not a number you need to memorize. It is on your formula chart. And then the temperature. The temperature needs to be in Kelvin. To convert from Celsius to Kelvin, we add 273. So now let's practice a little bit. I'm going to exit out so I can type. So I've got my equation. There we go. Because we're trying to find our solute potential. So it says calculate the solute potential of a 0.3 molar sucrose solution if the temperature is 21 degrees Celsius. So our variables, I is going to equal 1 because sucrose does not ionize. C, the molar concentration, 0.3. R, always the same, equals, and I've got my formula here again so I can see it. And then T, our temperature, is going to be 21 plus 273, which equals, let me grab my handy dandy calculator, 273 plus 21. 294 is going to be our temperature. So now I have to put those into my equation. And I'm just going to copy and paste that down here. And I'm going to have negative 1 times 0.3 times 0.0831 times 294 equals -1 times 3 times 0.0831 times 249 equals -73.2942. Now in the problem, they only gave us a decimal point up to tenths, so I'm going to round that. Here is our solute potential for this first problem. Let's come down here and look at our next problem. Calculate the solute potential of a 0.2 molar salt solution if the temperature is 23 degrees Celsius. So salt, so our ionization constant will be 2. C now equals 0.2 molar. R is the same. There's only 1 3 in that. And our T, we're going to take 23 plus 273, and this gives us 296 for our total. All right, so negative, it's going to be a -2 times 0.2 times 0.0831 times 296 equals, handy dandy calculator, -2 times 0.2 times 0.0831 times 296 equals -9.83904, but I'm going to round to just -9.8. So you've got the formulas and its multiplication. A fairly simple equation, and you'll always have it available to you. Next is the pressure potential. This is how much pressure is on a system. In an open system, the pressure potential equals 0. Open systems include both open beakers, which is what we will often be using, as well as cells, or most cells. Here in a closed system, molecules diffuse into a closed system and pressure against the boundaries of the system increases. The pressure potential value will then increase. Closed systems include plant cells that become turgid and dialysis tubes that have become filled. So in our little picture here, initially this potato cell had a pressure of 0. After a period of time and osmosis occurred, it increased. So let's work on graphing our water potential. All right, water potential in some potato cells was determined in the following manner. The initial mass of 6 groups of potato cores were measured. The potato cores were placed in a sucrose solution of various molarities. The masses of the cores were measured again after 24 hours. Percent changes in mass were calculated. The results are shown below. And so we've got the molarity of the sucrose in the beaker, and then the percent change in mass. So graph these data on the axis provided, and from the apparent molar concentration, and find the apparent molar concentration of the potato core cells. Let me escape out so I can edit this graph. I'll get myself a text box. All right, so my molarity is going to go on my x-axis. The molarity started at 0. Bear with me while I try to line things up kind of nicely here. 2, 6. Not something. 8. And then there's the 1. And I'm going to spread this out, give them 3s. Adjust my scale here a little bit, so I'm using up. This will be 8. There you go. There you go. Just stretch my scale out some. There's our molarity. On the Y will be the percent change. Start off. And I want to rotate this. All right. Well, it looks like I'm going to need to adjust some of my numbers. I will admit, graphing digitally is not the easiest thing. I'm going to backspace and hit my enter bar. Maybe do this every 4. 12, -8, -4. There's 4. Backspace, there you go. So this line's 20. That'll be 16. That's 14, so 12 is there. 8 is there. All right. I lost 8 there. Okay, I think we're close. Then on the other side, spreading it out. 4 should be up here, so it looks like 4. 8, 12, 16, 20, and adjust. Okay. Pen and paper is so much easier. All right. Now we're going to plot our data. This is going to be a line graph. Oops, so give me a line. At 0, our percent change was 18, which was up here. And it goes to at point 2, it was 5. So 5 would be about here. So there's the first portion of my line. 4 was -8. So here's, oh, let me grab a line again. 4, -8, and I want to come and connect it with my prior line. And then 6, I'm going to connect here, was down at 16. 8 was then at 0.235, almost to the bottom. And then here at 1, it was 24. All right, from our graph now, find the apparent molarity of the potato core cells. The apparent molarity is going to happen when, oh, I don't want that filled in, transparent. Let's make a nice bright line. where our line crosses the x-axis. So in this case, our apparent molarity, we can say is about 0.3 molarity. Once we know our molarity and when we know temperature, we can go back and calculate solute potential, which is something we will be working on more in class. You'll have a lab very similar to this one. I meant to make that not that big, a little bit. A lab similar to this using potato cores. And you're going to be able to figure this out by looking where it crosses the axis.